Good morning, everyone, and thank you for hosting me on this TRA session this morning. My presentation will be on envisaging smarter digital healthcare, now making it real. So my name is James Norman. I am the Healthcare Chief Information Officer for EMEA. And I work within the Dell Technologies practice of global industries. Okay, so what we're going to talk about today is the move from practice of precision medicine, how technology has fundamentally changed the way that we practice patient care. If we look at Michael Dell, who started Dell Technologies, he had an aim that we would transform the lives of 1 billion people. And healthcare is seen as one of the most important areas where technology can have an enormous impact. So how are we doing this? So if we look at some of the work that we've done in India, we invested in a digital healthcare problem that they were facing. And this was due to the poverty, where essentially millions of people were struggling to get access to healthcare services. We invested money and services working with Tata, one of our partners, to help over 20 million people in rural India get access to preventative healthcare. This is just one example of how Dell Technologies has invested in improving the lives of people over the last years. Now, why is this important in healthcare, and why is technology the driver behind it? Well, if we look at where we were and where we're going, we've seen a massive growth in the amount of data. Just to take an example, between 2016 to 2018, we saw a growth of 878%. Now, that is phenomenal. And we are seeing medical data grow by a massive amount each year. But the reason for this is the take-up in technology and looking at wearable devices, looking at digital pathology, looking at PACS images, your picture archive communication systems. All of these are digital and require storage, they require compute power, they require a new way of working. And it's technology that has really enabled us to leap forward in the way that we're providing care, to move from the paper record through to a fully digitized record. It's technology that is driving us forward. So which areas do we focus on when we look at transformation in healthcare? For Dell Technologies, healthcare is not one aspect. It is right from the edge, which is the computer that is being used by the nurse, the consultant, or at home and the patient and the wearable device, right through to the organization that is analyzing that data, and every step in the way in terms of whether that is captured in a central database in the hospital, whether it goes over a cloud provider, whether it goes to a third-party provider. We look at all aspects of this and how the data is managed and how the solutions are provided out to the patients. There are four key areas that we focus on. We find all transformation falls under these four pillars. The first pillar is around health IT transformation, and this focuses mainly on what we call our multi-cloud portfolio. This is where we are enabling organizations to work in a way that can connect the data across public cloud providers, private cloud providers, whether it's a hybrid model across the two, or whether it's combinations of everything. It basically gives you the power to look at where the data is sitting and across which media you're sharing that data. But to do so, you have to modernize your base infrastructure. And again, this is where Dell Technologies really helps people to understand what we mean by a modern infrastructure, one that is capable of working in a cloud, but also in a virtual way. And we often refer to this as a software-defined infrastructure. And we also work with partners who provide the solutions to optimize their clinical workloads. So this could be the electronic medical record providers, advanced medical imaging. It could be around genome sequencing. Essentially, we take them into our labs and we support the build of their systems to ensure that they run in the most optimized way. Now, it doesn't stop with the end supplier. We also focus heavily on what we call our connected health transformation. And the connected health transformation is where we work with the workforce to look at how they take advantage of new technologies. We look at how they communicate not only with themselves, but also with patients, with third-party suppliers, how the systems integrate with each other. We look at how they're taking advantage of Internet of Things, the healthcare Internet of Things, as we like to call it, where we're capturing data from clinical healthcare devices. That could be a device strapped to the patient. It could be a monitor in the hospital on the ward. Or it could be about the new ways of working using technology such as augmented reality or virtual reality, or even combinations of the both, where you've got information presented in front of the clinician as they're working and as they're actually carrying out operations. But they can practice in virtual reality to make sure that before they even start their operation, they are ensuring that they know how the operation is going to work in terms of the route through the patient, the operation itself, any details, any complexities. We also look at precision medicine. Now, by precision medicine transformation, we're talking about the use of big data and analytics, the use of artificial intelligence, machine learning, deep learning. And this is important when we're talking about the size of the data that we're capturing on a daily basis. We already mentioned about that data growth of 878% between 2016 and 2018. So we're talking very large data sets hitting the healthcare organization on a daily basis, too much for an individual to be able to analyze. So this is where artificial intelligence and deep learning kicks in and actually takes over from the human to analyze the data, to group it together and to find patterns. And when we look at high performance compute capabilities, which is looking at analyzing algorithms across millions of data sets in record time, this is ever so important because genomics and bioinformatics, the data sizes are astronomical. You need the capability of a high-performance compute and deep learning and artificial intelligence to make sense and recognize the patterns within the data and actually identify where the problems lie when you're analyzing that data. And the same goes for digital pathology, which is about scanning the slide and presenting a digital representation on the screen where you can start to overlay pattern recognition and use artificial intelligence to recognize tumors or anomalies for quick identification, quicker diagnosis, and better outcomes for patients. Now, all of this is important in terms of the actual systems, but more important we're finding nowadays is the application side. And this is about the interaction with patients, the use of new technologies through mobile devices to communicate with staff, with patients, with third party, to capture data around the environment. This could be sense and economic and environmental data. All of these can feed into the understanding around what's happening to a patient. And as part of this, we work on capabilities for individual teams in terms of their DevOps, their data science capabilities, how they actually go about creating the application, how they rationalize the number of applications they have across an organization, and how they integrate those applications into existing systems and create a capability for interoperability across multiple systems. And it's that latter part which is so crucial nowadays, because as we've seen over the years, clinical systems have grown up in isolation of each other, not being able to talk or share information. Now there's a big push on being able to create that seamless move of data across all systems. So being able to understand how you do that integration is essential. Now, I mentioned MultiCloud, and when we look at new sources of data and emerging technologies, the MultiCloud is the one which most people seem to be taking to heart at the moment. And by this, I mean they are looking at how they can extend their capabilities, not just within the organization, but across multiple organizations, nations, geographical locations. This means they have to work in a different way. Now, this could be through the use of what we call our public cloud providers. It could be through the use of private cloud providers. This could also be a hybrid or a mix of all of the above, where you keep sensitive data on the premise of the hospital and you only share the application out over a public or a private cloud to make sure that sensitive patient data never leaves the organization. It's about enabling the capability of all of the above. And we're finding that on average, most healthcare organizations are now looking at a combination of 3 to 5 different cloud providers based on their needs, whether that's to take advantage of the compute power that could be provided, whether that's to take advantage of the analytical tools, whether that's just as a security overlay to govern identity and access to data, or whether it's to provide cheaper storage for the archive of data that's being held around the patient. Now, all of this is critical when you look at the rise of digital electronic medical record systems. This is where all of the patient's data is being pulled together into one visible system that clinicians can use to treat and diagnose patients. And what we're finding now is with the advent of technologies such as 5G for mobile apps to increase the size and reduce the latency of capturing data and enabling more data to be captured via mobile apps, we are able to take advantage of what we like to call edge compute and IoT devices. Edge computing is where you're pushing the analytics down to the end device. So this could be the wearable device by the patient, whether that's a digital plaster capturing early warning signs, whether that is a medical device in the form of a smartwatch or a device which goes on the wrist that just captures system data. So all of these are important because when you start to capture more and more data, to move that data from the patient to the hospital creates a latency, so a lag in the data arriving. And what we want to get to is near real-time information to be provided back to the patient and near real-time alerting to be provided to the clinician so that you can monitor patients' conditions outside of the hospital. And finally, the other technology we're seeing emerging is around advanced medical imaging. Advanced medical imaging, such as digital pathology and radiology, but also cardiology, is where we're starting to see real-time activity happening, where people are monitoring the patient's arrhythmia or their slide and being able to look at how they can overlay artificial intelligence, machine learning, deep learning practices to understand the patterns or to look at the rhythms and actually take action on the back of that data and alert the clinician to what's happening. Now, these technology trends are accounting for a lot of focus. And when we look at the healthcare cloud, this is by far one of the biggest growing areas that we're seeing. And in fact, from the HIMSS analytics survey that was carried out recently, they are forecasting that up to £55 billion dollars will be spent on healthcare cloud computing by 2025. Now, when we also look at the amount of data, and I mentioned earlier that in between 2016 and 2018, we'd seen this massive growth in data of 878%. We're now seeing that this data is doubling every 73 days. Now, if you look at the growth just over that 2-year period, you can see the requirements for storage moving forward and for increased compute power are going to be ever more important to be able to take advantage of the data. Now, the market value of the Internet of Things is what's really driving change. People are seeing the growth in the likes of smartphones, in the likes of smartwatches, in the likes of smart devices. This could be clinical monitors, it could be a bedside monitor, it could be a heart monitor, it could be a blood oxygen monitor. All of these clinical devices and medical devices can now be connected digitally to provide live streams of patient data that can be captured into the EMR, and action and insight can be taken on the back of it. And this is just going to grow. And we've seen this trend now happening over the last couple of years, and is really taking off. And by 2025, we expect the market value of this to be around about $257 billion. But it's not all about increased cost. We're seeing the rise of artificial intelligence and machine learning result in new ways of working, in reducing the time it takes to analyze slides, to analyze the data, and to create the capabilities to make huge savings per year. And McKinsey forecast that we would be saving on average $100 billion per year just from the use of artificial and machine learning. Now, that's currently, if we apply. If you look at the amount of data doubling every 73 days, you can see how those savings will continue to increase. Let's take a look at precision medicine, or personalized medicine, as we sometimes call it. This is where we are creating a fundamental change in the way that we look at patient care. And we're actually looking at care that's directed to the individual rather than to the whole population, which is how we would look at medicine in the past. Basically, precision medicine looks at formulas, it looks at drugs, it looks at individualized pathways of care that works for an individual rather than just for 85% of the population. And if we look at the new technologies that are being used, such as genome sequencing or whole genome sequencing, next generation genome sequencing, these are things that weren't available 10 to 12, 15 years ago. In fact, if we look back 10 years ago, it would take up to 10 years and $3 billion to actually sequence a whole genome. Now the technology allows us to look at next generation sequencing within 1 week at a cost of $3,000 per genome. And we expect that trend to continue as new technologies and new compute capabilities come on board. The next generation sequencing, or NGS as we also like to call it, can take advantages of other technologies as well, such as digital pathology, to work alongside it. And bringing these different technologies together and these advancements is what is going to make it easier for healthcare professionals to provide personalized and individual treatments based on better knowledge and a better understanding of what is happening to the patient. Now, medical imaging has come along in heaps and bounds, and medical imaging is now no longer just the X-ray. it is your medical resonance imaging, it is your CT scans, it is your X-rays, it's your sonograms, it's your mammograms, it's bedside imaging, and it's even pathology now. So we've started to encompass a number of different areas of focus by clinical professionals, and we've brought them all together, and we've created a capability where you can use the data alongside each other to make a better diagnosis. Now, to do so is not easy, and in fact, it requires different capabilities to bring these together into a common way of viewing the data and also reporting on it and making sure that you're able to understand the movements and the changes in the patterns. And to do so is important because it isn't as easy as simply moving from one area to another. What we're finding is you have to have different sections created. And if we look at one of the departments, so the picture archiving and communication system, these are the first phases that we've seen of people actually creating digital capabilities within hospitals. And they've certainly been amongst the most successful because they've removed what we called the light boxes, which was literally a light viewer on the wall which just shone light, and you had to put the old X-rays up against it, make a clinical decision based on very old technology. Very difficult to actually zoom in and make sure that you were happy with the actual diagnosis. A lot of it was best guess based on experience. So now we've moved it to a digital capability. Obviously, what you've had to do is look at how people are going to look at the data and what we call our referring client viewers. These have to be very high resolution because you're going to be drilling down to the minute level just to look at fractures that might not have been visible to the human eye previously on an X-ray sheet. You're also going to then have what we call departmental viewers. This is not going to be used for diagnostic purposes in most cases, but where you're going to make the data available to the more generic capabilities of clinicians across the hospital and healthcare organizations. Typically, these would be cheaper devices, still high resolution, but you would be having larger screens to capture more data and to make it more visible to see the reporting that's been provided by the diagnosing clinician. And underneath all this, you would need to focus on the storage of the data and how it works and the systems that run on it. And for all of the different departments, you would be focusing on the same type of approach. High resolution viewer, departmental viewers, and then storage and compute for each of the systems, all in isolation. But how you digitize and bring these together, you have to go through a step of consolidating what we call these archives. And to do this, you have to create an enterprise archive across all the systems. So you bring the data together from your radiology, your cardiology, your other clinical PACS devices, and you create what we call a vendor-neutral image solution or vendor-neutral archive. This enables you then to overlay different software packages on storage without having different replications of the data. So rather than a single storage array for each department, for radiology or for cardiology or for ophthalmology, for example, you have one storage array that now provides a universal capability to be viewed on one system. Now that improves the amount of time a clinician has because they're no longer having to move from different system to find the patient that they're looking at and make sure that that patient is consistent across all systems. They're able to bring in context management and look at all the different data associated with that patient. Now, the emergence of digital pathology and imaging workloads for healthcare and also for research has been one of the best innovations in the last few years, because it's allowed you to overlay your pathology slides to look at cancers, to look at tumours, with the genome data. And when we look at digital pathology, we talk about whole slide images. This is your WSI. And what we mean by this is where you're actually digitizing the whole of the slide. Typically, when you look through a microscope, you will focus in on just one tiny area. And the reason being is because you're looking in such high resolution that humans just have to try and create a pattern out of where they think the anomaly on the slide is. So you will use dyes to change the color to make the resolution different and to also pick out specific tumors. They will look at different sections and focus in on tiny areas of a slide. However, when we digitize, we can digitize the whole of the slide itself and not worry about missing patterns that could typically be missed by a human or that might take a long time to actually get to the slide, to the tumor. But to do so takes a lot of data storage because the resolution of these slides is so high that you are creating file sizes in the terabytes of data, which is a lot more than has been done in the past. But once stored, these digital images can open the door for artificial intelligence and machine learning analysis. And according to a study that was carried out by the AI or Pathology to leverage AI to help them analyze and diagnose where more accurate data in their findings than just the pathologists alone. Therefore, by working with artificial intelligence and machine learning, doctors have been able to prove that they can provide better care. Now, concerns have risen about doctors becoming dependent on artificial intelligence. So we're now seeing new practices being built into the process to help understand how to use digital pathology, not as the end solution, but as a support mechanism for pathologists. What we're seeing here is a capability now moving from what was the glass slide, which is where typically they would take a slice of the tumour and they would process it, create the dye, put it onto the slide and look at it under the microscope, to new systems that can do the whole slide imaging. And these are scanners which are very, very high resolution and can digitize hundreds of slides in a matter of minutes. This slide, however, then needs to be put into the central storage, and this is your whole slide image archive, your digital slide storage. Typically, you would do that on a scale-out storage capability. The reason being is because you don't want to be having any downtime for clinicians by moving from one storage array to another when it fills up. So we are seeing digital pathology take on the scale-out network of attached storage capabilities so that they can continue to grow and grow without any loss of performance. But of course, you also need to bring in archive solutions to move the data off into deep storage, and you need solutions that have a capability to move that data between your live data to your archive. This needs high processing capability, however, to be able to run the artificial intelligence, the deep learning, the machine learning on the patterns. And here we are typically seeing not your CPU, but your GPU servers that allow you to do lots of processing simultaneously over pattern recognitions. These then have to be presented into image view and search for the labs to be able to make the diagnosis, but also across into the electronic medical record systems, no matter what they are. So you need the capabilities to create an interoperability link into the different systems. Unfortunately, even though we talked about the importance of DevOps and that application transformation at the start, this bit here really is still the glue between lots of clinical systems who are still playing catch up on all the different data standards that are out there to enable the data to move from one system to another. Now, artificial intelligence and machine learning has really come to a very important stage in the process of moving forward precision medicine and enabling healthcare to advance. And this is because it allows you to analyze real live sets of data, large sets of data in real time, to create alerts, to create diagnostic supports, to ensure that the patients are able to understand if they need to take action, but also to alert the clinician if they need to contact the patient. And this could be because their early warning scores are starting to deteriorate, or we've seen their heart rate start to go outside of set parameters, which is creating an alert. This is all being done at the edge, at the patient level, where the device itself is actually doing the diagnostics and is pushing that alert back to the clinician. But also, we're seeing machine learning for disease identification and risk stratification, and especially deep learning in the disease identification, where it's allowing it to look at specific patterns, which is an advanced form of machine learning. And that risk stratification is where we're predicting the outcomes for patients. And we're now seeing systems able to predict when a patient is going to suffer a heart attack within the next 5 to 10 minutes, or some sort of severe reaction that requires interception now from a clinician in order to prevent that. And this patient triage optimization is really where we're seeing the benefits out on the wards and for healthcare professionals, which is supporting them to provide a better level of care to patients, because there is consistent monitoring 24/7. That means that then patients have been monitored 24 hours a day, 7 days a week, without the individual nurses or clinicians having to stay by the bedside and consistently monitor. And this is what we call the proactive health management, where we can support not just in the hospital, but outside of the hospital. And healthcare can actually bring in what we call sentiment analysis. And this is looking at the environment that the patient actually lives and works in, to look at social media tools to understand how the patient is interacting with society, to understand the stresses on the patient and how that's impacting on their healthcare. And artificial intelligence is everywhere. However, it is not the silver bullet. So we do not rely on AI to provide the final diagnosis. The reason being is because it still needs a clinician to qualify and understand what's happening in there. And the reason for this is because we're still improving the data quality and where we're capturing the data. And at the moment, although AI may be able to provide a higher level of accuracy around digital pathology, we still need the digital pathologists to make sure there are no false positives in there or any problems. And we also need the pathologists to overwrite if there seems to be an issue. Now, it's all very well as doing that, but we do need to make sure we've got the quantity of data to give that rounded model for providing an overall diagnosis to patients. And if we look at this capability, there are very few organizations who can provide a capability from capturing the data right at the patient level through to the diagnosis, through any provider who is moving that data in the telecommunications right to the clinician and able to do the artificial intelligence on that. Now, if we give you an example of an end-to-end data analytics process, you can see all the different points that artificial intelligence can support on the interaction. You're looking at customers. These are the business users. These could be the analysts. And you could be looking at how you can use data strategies, use cases, create roadmaps, engage with value stream analysis. You need your data scientist, who is an expert on statistics and mathematical models. They understand the artificial intelligence and they understand the use of new languages like Spark or Python or R or SAS, where they can take advantage of these languages to analyze the data. And they can create that data into new mathematical models to look at risk stratification and to understand the patterns that are being created from the data. They can then share that data with the end users to look at how they can consume the data into different applications, creating what we call a data lake of data that the high performance compute can run on to provide near real-time accuracy in the data, to get data, more detailed understanding of how the data can support precision medicine, how it can feed into different applications, and how new applications can take advantage of the data. But then that opens up for solution architects to create new capabilities such as end-use devices that can link via the Internet of Things, Hadoop ecosystems, new database capabilities, microservices, federated data where you're sharing the data across multiple databases to reduce that load on the information. Where we've got developers and Hadoop ecosystems, Java, Python, JavaScript, databases, microservices, all these capabilities to improve the way that you create applications. And we're seeing containerization where you're breaking the applications down into repeatable modules that can be shared across different applications, now becoming the norm. And the likes of Kubernetes to actually manage all those different applications and the different containers within as you start to build hundreds and thousands of different iterations of your applications, all taking advantage of the data. And when we talk about DevOps, development operations, we're really looking at that whole end-to-end spectrum, from the infrastructure to the code to the teams to how you can take advantage in terms of the architecture of the data to provide that out to all of your end customers. And if we look at accelerating the analytical value cycle, typically there are different states. When we look at the data discovery and preparation, there are a number of problems that people can find. Typically navigating the data silos, because the data has typically been held in different databases, whether that was for your digital pathology, your cardiology, your ophthalmology, your PACS. There could be multiple databases, none of which were talking to each other previously. So being able to understand correlations in that data was difficult in the past. Also, the ability to apply metadata on top of this and create a capability to trace the lineage and the correlations between the data across multiple data sets. You also had to spend a lot of time cleansing and integrating the data and normalization of that data to allow your analytics processes to run on the various data sets. And in doing so, there was all the issues that you would find around patient privacy and compliance with local policies and local laws around how the data could be viewed or interacted with or taken advantage of for research, etc. And this used to be weeks, if not months, in terms of the data process that took advantage. And when we brought in artificial intelligence and the development of machine learning and selection, we had problems with the workload contention, the lack of tools, the flexibility of those tools, because it was such early days. We had to manually set up the environment and request that environment to work and then create a setup process. We had to do the repeatability of results, and we had a lack of data model sharing. And again, it took weeks. And the application development that was on top of that, we saw a lot of people having to rewrite the application every time, commit to the application before they moved it to the test process, then run the test on dummy data, and once they were happy with it, deploy it. Again, they created things that could take weeks, months, sometimes even years. We weren't creating value, and what we were talking about was a cycle time of months. What we have done over the last few years is we've created capabilities, what we call data as a service, and we've turned that around to self-service data portals, searchable metadata across all those data stores by creating these archives of data where we're pooling all the data together into a single repository. And we're enabling the new languages to run across those, where that data virtualization and data collaboration has moved the process from weeks down to hours. We've changed the capabilities of artificial intelligence to enable it to run as a service, as an analytics platform. This means you can self-request different portals, different environments to work with. You can work across multiple tenancies. You can bring new models, new data versioning in, and basically you can integrate your data and your data sandbox to the live data to do real-time testing and analytics about that. And you've got new processes from the CPU and the GPU to help it. And when we overlay artificial intelligence as a service, we're seeing that final process going from deployment of new applications being months, if not years, down to days. Sometimes we're seeing iterations of applications happening, 3 or 4, maybe more times a day. If anyone's seen the likes of the iOS operating system for Apple or the Android system for Google and different devices and the Microsoft's capabilities as well, they push out new iterations of their code throughout the day. Sometimes, they'll find there's a problem and they can roll it back to a previous version almost instantly. This is that capability that this gives you around the automated streaming, the API integration and movement. Target cycle has now moved down to days. And part of the capability here has been new technologies like 5G, reducing latency and allowing networks to will reduce the latency commonly found on the 4G networks down by 95%, down to 5 milliseconds. And when we look at things like new IoT devices, when we look at the history of IoT can capture data from any device, and we use it for measuring things like, take it for example now, the coronavirus and the COVID-19 impact, where we've been able to capture data from all the devices in different hospitals and sensors to understand the impact on human life. But if we were to go back to 1980, here you can see a picture of the earliest Fitbit. That wasn't actually something wearable, but it was the first IoT type device capturing data at the edge. So you can see how things have moved on. And nowadays we are seeing between 10 and 15 typically connected devices in a US hospital. And we're also seeing that, as a result of that, the medical data will double every 73 days, creating what we see as 25% of all data now being captured via IoT devices. Now, the future demands edge analytics because of the volume, the speed, and the uptime needed, to capture that data. However, really, it's difficult to show how that can help in practice. So I wanted to give you a very quick overview of a hospital that has taken this into account. So this is a case study of virtual care, which is being run in Mercy Health, which is a St. Louis virtual care facility. They are actually running 44 acute care beds and specialty hospitals with over 700 physician practices, 2,000 physicians, 40,000 employees, and yet they don't have any beds of their own. This is done through 160 workstations where they monitor the vital signs of patients, of over 10,000 patients daily, using biometric sensors. This has resulted in a 15% reduction in hospital admissions and a 20% reduction in medical spend, with significant improvements to the patients. So we're now talking about how the transformation pillars have actually brought everything together. They're underpinned by security along the way, but health IT, precision medicine, connected health, and applications, all underpinned by security, is really how you go about transforming and creating a digital healthcare practice and making it real. Thank you. I hope you enjoyed that. I'll now answer any questions that you have. So please, if you pass them via YouTube, I'll pick those out. So if you have any questions about the presentation, please just add them to the chat in the YouTube. you have any questions on the questions that was pushed out previously, I'm happy to help you and take you through the slides. Hopefully you were able to answer all the questions correctly. But as always, you know, if any were confusing, I know some of the numbers seem quite large, but this is the size and the speed of the trend. So there's a question or a comment made here about medical records stored in IoT, and are they vulnerable to hackers to be used for illegal manners? So the patient's records currently do not get stored in the Internet of Things devices. They send the remote data down as anonymized data, and the IoT devices can be used across multiple patients. However, when you're doing a diagnosis on this, it's absolutely critical that you understand that full end-to-end process. And this is where Dell Technologies, and I go out and I talk to people about the concerns on using IoT devices, which is you really must understand that full data transmission from where the data is captured, the security in which it's then passed back to the system that makes the decision about the patient's care. And you need to secure the full end-to-end. So we have technologies that enable that, but there's also a series of processes to support the governance around this. And again, this is where we help organizations to understand that it isn't as simple as taking data off a website and assuming that it is correct. And you're absolutely right, but if you do that, you expose yourself to higher risk because people can intercept that message and the website. So you have to own the full end-to-end data. So a question here about the impact of digital healthcare on the quality of treatment. So we are seeing faster diagnosis through the likes of digital pathology, and studies have shown that when using artificial intelligence to look at pattern recognition on a digital pathology slide, the artificial intelligence had a higher accuracy than the clinician. This means if you were looking for, say, a cancerous tumour, there is more chance of a clinician without using an artificial intelligence to miss a tumour than there is when the clinician is using artificial intelligence to support them, because the artificial intelligence will look for anomalies and find patterns that the clinician might miss due to the fact that the clinician is looking through it in the old ways before it was digitized, would be looking through a microscope and would only be able to look at part of the slide at any one time. Whereas the artificial intelligence and the whole slide imaging can look at the whole slide and create patterns and identify areas that might have got missed previously. We've also seen with the impact of electronic medical records, studies done with clinicians. When I was a CIO previously, I did a study internally in the hospital to look at the impact of using a medical record going back 10 years ago, where we identified that for each outpatient clinic that was being run, on average, we were saving an hour or 30 minutes to an hour per clinic for each clinician. Now, a clinic might run for 3 or 4 hours. Typically, you would be reducing the amount of time it took to actually pull together all the relevant information for clinicians to make an assessment about whether the patient's condition has improved, deteriorated, or whether they need to change the treatment that the patient is on. Previously, they would have to go through medical records and they would have a lot of stress trying to remember all the history when they're seeing lots of patients. So it's improved the efficacy, it's reduced the stress on clinicians, and it's improved the outcome for patients and reduced risk. Just looking through some of the other questions. Lots of thank yous, and it was my pleasure presenting to you today. So the question about how digital records work in treating the patient, essentially what we are talking about here is bringing all the relevant information that a clinician would typically need for to make a diagnosis or to understand how a condition that a patient has been progressing and whether treatments are actually working or not. What we need to do is make sure that we don't overload the clinician with too much data, because you can actually have the opposite effect if you do that, which is you can confuse the clinician, or you can move them to actually make a false diagnosis. The reason being is because when you overload a clinician with conflicting data, which you might get from different systems, the clinician then doesn't really, he starts to question their own approach and whether their pathway of care is appropriate. So by ensuring you get the right information and that you understand what data you're capturing and how the different data correlates together, and this is where a data scientist and someone who's got the experience of working with the data really needs to be involved in pulling those electronic medical record systems together. This enables only the valid, relevant information to be provided to a clinician, so that there's no confusion. They can instantly get to the data they need to understand how the condition is progressing, whether that's for the better or worse, and also the impact of different drugs and treatments against that condition. They get the information, they can actually start to get that information in real time via IoT sensors, where they can now communicate with patients outside of the hospital environment to understand how stressless environments, because going into hospital can cause stress to the patient, and can actually create a false treatment pathway, because you're not treating the patient as they would actually react in their normal home environment. And you have to account for that normally when you're in a hospital. So if you are monitoring them outside the hospital environment, you get a much more accurate picture about what's actually happening to them to make a decision. Okay, so question about COVID-19 and how difficult it is to trace vulnerability to the virus. Do you have applications to immediately trace this pandemic? So we have created a track and trace application that has just been rolled out by the UK government. This is going to be made available to other countries once it's gone through testing, and this will enable you to do contact testing between mobile phones. Obviously, it is going to be subject to the different technologies and capabilities in each of the different countries it's being used. As I said, this is just being tested at the moment. We've also seen the likes of Google and Apple enable low Bluetooth contact tracking in some areas. There are obviously concerns about the use of data in some countries, and about patient confidentiality. All of these issues are being looked at the moment. But we are seeing the use of mobile devices and sensors as a way of being able to track. We're also seeing the use of infrared cameras to do fever detection as a way of helping to identify people who are starting to show signs of the coronavirus and COVID-19. Obviously, the problem with COVID-19 is and the coronavirus is you could be asymptomatic, which means you can be a carrier and contagious, but not show any visible signs and not feel unwell yourself. So there are new technologies coming out which can do swabs in under 5 seconds, give you a result back to say whether you have a pathogen or not, and these are using ultra detailed scopes to look at the sample And rather than give an actual confirmation you have COVID-19, they can tell you whether you are actually contagious with a virus or not. These are probably going to be used with fever detection camera systems and situational awareness systems, such as ones that Dell Technologies provide as well, and capabilities to help monitor outbreaks and to bring retail and services back online in the coming weeks and months. See if I've missed any more. Do I think it will be mandatory for every person to have a human microchip implant that stores all the information about the person, history, sickness, etc.? I don't think it'd be mandatory, although we are seeing microchips be used on voluntary basis by individuals, and they have tested the information. Obviously, we know it works. We've seen microchipping of pets be used for a number of years to store minimal data, such as the owner's details and the contact number and the name of their vets. We've also seen devices for humans which are able to interact with sensors that can give a specific user code that is unique to the individual, so that it can be used instead of payments, or it can be used to turn lights on, to gain access to buildings, etc. We are now seeing overlay sensors that, rather than having to be embedded in the skin, can be applied like a tattoo. And again, it's powered by the heat and the sweat and the salt of the skin, and that can be used as a sensor in its own right as well. These technologies are emerging, and we will see them continue to emerge as we progress, and as technology and the use of nanobots and nanotechnology gets more and more advanced. Okay, we're coming up on the hour. Are there any more questions? I hope I haven't missed any. How can I take a degree? There are courses in data science, if that's what you're talking about. These courses are now typically run by most universities. The rise of data science has been quite significant over the last 5 years. Dell Technologies, we run courses with our customers as well. So we can support organizations in this. We see this important, being able to train the users of our technology to ensure they get the best out of this, and also to help them develop. So that is something that we can also help you with. Okay, I think we can close there. So thank you very much for your time. I hope you found it useful and informative, and hopefully I'll be invited back to do one of these again in the future. Thank you.